So nice to meet you all, and what a great society, Neurotech. So I'm a physicist by training, so my first degree was in physics. I did a master's in neuroscience, and since then I've kind of worked on the intersection between physics and neuroscience. So hopefully matches your interests quite well. And so I'm a professor of neuroimaging here at the university. And I thought we'd just sort of tell you a little bit about what MRI is. I mean, I don't know what everyone's background is, but maybe just a bit of information. Yeah, maybe just saying where you're from. So
we have psychology,
great.
Neuroscience, mostly. Yep.
Yeah. Is there anyone non-brain? Unfortunately. Okay.
No.
Does anybody not have a brain?
Wasn't going to ask that.
And anyone more physics engineering, or is it really mainly neuroscience? Like, yeah.
But also, we started this year and haven't advertised it.
Okay, yeah, no worries. But yeah, no, it'd be nice. It's always a nice, because Natalia did a couple of weeks, didn't you? Yes. Summer school with some of the physicists, and I think you can really learn from each other, I think. But this isn't physics heavy, you'll be pleased to know. There's a little bit in there. So yeah, I thought I'd tell you a bit about MRI and just a flavour of some of my current research. And then maybe perhaps the most interesting bit is just a little bit of my career path, because I'm guessing you're all at a point of thinking of doing PhDs, masters, etc. So, which I would highly recommend. So MRI, this is my favourite. I'm sure you've all seen this a million times, well, Caroline has, but this is one of my favourite movies, which just shows you a pretty standard T1 weighted image of the brain, actually, but just highlights, I think, why MRI is so useful for looking at the brain. So it's, if I stop it at a good point, you can sort of see, maybe there, oh no.
Isn't very tech.
No, it's not very tech, is it? Oh well, you get the idea. But you can see problems with tech that we need you guys to solve. Yeah. So let's just get it going again. Yeah, but you can see, I think, that there's very nice contrast within the structures of the brain. So you can see very clearly the structures, and there's no other technology which allows you to do this, really. So EEG, MEG, they'll allow you to sort of measure the electrical activity from the brain, but you can't get this kind of an ambiguous localization of activity. And you can acquire this kind of information in about 2-3 minute scan now. So nearly everyone, all the studies we have going on at the university scanners now, everyone will be collecting this T1 weighted image. And there's really big databases of studies now. I know you were interested in perhaps getting some data. I need to think about that. But the UK Biobank, will have hundreds of thousands of these kinds of images. So it just allows us to start to study the population rather than sort of smaller individual studies. So how does it work? So I don't know, has anyone had a scan? We never got you in the scanner, no? You have? Okay, good. Yeah, how did you find it?
Interesting. It's quite quick, and it's very early in the morning, so it's like can't fall asleep.
Yeah.
So,
yeah.
Not too much of difference from lying to bed.
Yeah. Okay. Yeah. So people kind of find it differently, obviously, depending partly on kind of why you're having the scan. If if you're taking part in a research study, it's maybe different from having it for a medical reason. But you basically get sort of wheeled into the big scanner, and then you have a head coil placed on top of the head, which detects the signal from the brain. We can scan the whole body, but you just need the coil in an appropriate place to get signal from all over the body. Don't know what, it's very noisy, that's perhaps the other thing to say here. So you notice that he was putting like earphones in, maybe I'll just play that again. Which is really critical because it's extremely loud in there. So the main reasons people don't really like getting the scan is the sound and the claustrophobia. But apart from that, I think it's reasonably pleasant experience. So how does it work? So we've got this big tube that you go into, and that is creating a really strong magnetic field. And it interacts with the atomic nuclei in the brain. And I'll explain that in a bit more detail. And the head coil there is receiving the signal from the brain. I mentioned that. And so you can sort of see a cutaway of the scanner there. It's a little bit small, but it's basically just coils and coils of very densely wound copper wire, which is actually supercooled to using liquid helium, which means we get a really strong electrical current flowing through there, which creates the magnetic field through the bore of the scanner. And it's partly why MRI is quite expensive, because you have to refill the helium, so every year it will boil off. They're trying to develop new scanners now which have zero boil off, which will make them cheaper, but also helium's running out, so this is one problem with MRI. What else to say? Yeah, and there's a move towards going to higher and higher field scanners, which will increase the general signal to noise of the image. So where does the signal come from? So the reason we get such nice images from the soft tissue in the body is that we're getting the signal from water molecules, shown here, and in particular from the nucleus of the hydrogen atom on the water molecule. And this is just a single proton. So it's positively charged, which means it'll be affected by the magnetic field, but also it's got this property called spin, which is an intrinsic property of that particle. And you can kind of imagine that it's spinning. But because it's charged and it's spinning, it means that this acts a little bit like a bar magnet. So when you place it in a field, it will be affected by the field. It will try to align with the field in a sort of crude way, although obviously this is on a real quantum level. So then when you place all those protons into the magnetic field, they'll interact with the field. And actually what they do is, so each proton will have like a magnetic moment, which is aligned along the axis of spin. And when you place it in a field, it will try to align with the field, but what actually happens is it starts to precess around the field. So it's very like a gyroscope in the gravitational field. So it's almost, you can think of it as very similar to this. So if you've got a mass that isn't spinning and you put it in a gravitational field, it'll just fall over. But if it's spinning, it will start to precess around the gravitational field. So the protons do exactly the same thing. This video isn't working, but it's not very exciting anyway, this video. But basically, these protons in the hydrogen atoms will start to precess around the magnetic field. And it's that you get your signal from. So if you can get all of your protons to precess together, you can create a measurable current in a coil, and so you can detect that signal from the water in the brain. So without going into a whole load of detail about MRI, that sort of is a nutshell of what you're getting. So if you're in the scanner, you've got your head coil over the head. You manipulate the system without going into too much detail. You manipulate the system so that you've got all of these protons processing together. And then you place, the head coil then will detect that processing electrical field, and you'll measure this oscillating voltage in the coil. So that's the basis of your signal. So it's coming from the hydrogen atoms or the hydrogen nucleus in the water molecules, which is why it's such a useful technique, because if you think about other imaging techniques like X-ray, it's kind of being stopped by bone. You're not getting a signal from the tissue itself. So it's really one of the best methods for that. And then this obviously isn't an image. Like, the next thing you need to do is sort of assign this signal to positions in space to form an image. And you can do that by slightly changing the magnetic field with position. So the frequency at which this is oscillating directly depends on the magnetic field strength. So, if your magnetic field strength is the same everywhere, you're not going to be able to sort of position this to different parts in space. But if you slightly change the field, it's like your frequency tagging the signal. And then you can say, okay, that signal comes from this bit of space, and you can build up an image. So that's like the basic concept of building up an image, really. So we call them magnetic field gradients, which just means the field is changing with position. Yeah.
When you change the field, does it change throughout the entire MRI scanner? Because it's all one coil.
So there's additional, that's a really good question. There's additional coils, the gradient coils, which control this additional change in field. So you've got your main field of the magnet with the coil, and then these extra coils, and they're such that you can put current through X, Y, or Z coils and change it as you like from scan to scan. And so that means you can sort of position the slices wherever you want in the magnet, orient them, and so forth. Yeah.
And it's kind of like constructive interference, or not exactly.
I think I'd think of it more like, it's called sort of frequency encoding. So you're just encoding the signal according to the frequency. You're not having to do any reconstruction or deconstruction. Well, you have to do some reconstruction, but unlike EEG, where you're sort of doing an inverse problem, I don't know if you know very much about that, where you don't have a unique solution. With MRI, you know exactly where that signal is coming from. So it does enable you to sort of locate signal precisely. Yeah.
Just from like how do you discriminate between the field that's obviously the big solenoid that's generating? Is it like switched off and then like you look at the thing,
No.
or are you just able to?
Yeah. So that main field is always on because it takes a lot of power to ramp it down to the liquid helium temperatures. So you're maintaining that field. And so these fields are just superimposed on that main field, really. So, the proton will experience the sum of both of them. Yeah.
Okay.
Yeah. Good question. Any other questions? Okay. So I'm going to get onto some nice pictures in a minute. So that gives you an idea, I think, of where the signal's coming from and how you can locate it in space. And one other thing is the rate at which the signal decays is depends on the tissue, depends on the environment of the tissue. So this is actually so-called T2. It's an exponential decay with time constant T2 star. So if you learn more about MRI, you'll learn about like T1, T2, T2 star. But this is perhaps even just to first look at that. So this decays according to T2 star, and that will depend on the tissue where you are, what else is going on around the water molecules. And in particular, if we've got neural activity, so I'm not going to talk much about fMRI, but if we've got neural activity, we'll get a change in blood flow, which changes the amount of deoxyhemoglobin in the blood. And that distorts the local field. And so if you've got a lot of deoxygenated blood, this will decay a lot quicker. If you've got increase in neural activity, you're washing away that deoxygenated blood, you'll get an increase in the signal. So that's kind of like the basis of fMRI. But I mentioned this also partly because you kind of can choose at what time you sample this signal. And so you can decide whether you want your signal to depend on this decay rate or not. So whether it's weighted towards T2 star is kind of the jargon we'd use there. And so you can control the contrast that you get in your images. So just gives you a flavour of that. But there's lots more to it than that. There's lots of things you can change, not just the timing of when you collect this signal, which can give you quite different contrasts in your images. So I've just got some examples now of the different kinds of images you can get. So we've already seen like a T1 weighted image. So these are now just sort of slices through the brain here. But you can also get what's called a T2 weighted image, where the signal depends on the different T2s of the tissue. And I suppose the thing here is the images look completely different. So you have like really quite a lot of control over how you manipulate the scanner. And there's endless sort of possibilities here, really. So we can look at the blood vessels. So this would be actually injecting a contrast agent, which changes the magnetic properties of the blood, and so you can be sensitive to that. You can look at the veins. So this is actually taking advantage of the fact that the deoxygenated blood, the signal will decay more quickly, and so it's black. So it's using that T2 star weighted contrast. A couple more cool ones. So flare is a bit like this one, but we've squished we've suppressed the signal from the CSF, and so you can sort of more clearly highlight these white matter lesions around the brain. So this is a sign of cerebrovascular disease. Last one, my favourite one, is just to remind everyone that this is a really safe technology. So this is a baby in the womb at 26 weeks. And it's amazing. You can see the brain. You can actually study the development of the brain in a fetus, and it's completely safe to do that. This is actually my daughter. Did you know that? Yeah. Okay. Yeah. She's like a teenager now, getting a Spotify rap. but yeah, she was cute once. Yeah. So I like that one. Okay, so that gives you a bit of an outline about MRI. I hope I'm not taking too long. No. So just wanted to give you a flavour of kind of the research that we do in my lab. So one real focus is looking at cerebrovascular disease and trying to quantify blood flow in the brain. So we're trying to quantify lots of different properties of the microvasculature. Partly because this is not very high res, but you can see how densely vascularized the brain is. So it's full of neurons. It's also full of blood vessels, and more and more we're understanding that there's damage to the blood vessels, which underlies quite a lot of disease processes. And obviously the neurons really depend on the blood flow. So this is a bit physicsy, but there's a technique called arterial spin labeling that we've worked a lot on in the last 10 or so years, where we're taking advantage of the movement of the blood. And so we're able to magnetically label the blood water. Remember, the signal's coming from water, and then you can then track that labeled water as it travels through the brain. So you can get a series. It's also quite poor resolution, but you can get, this is with time, as this labeled bolus of water is traveling through the brain. So it sort of, you can't see very well there, but it sort of starts in the larger vessels, moves into the brain, and then it'll also start to decay. But a lot of my work is about collecting quantitative images like this with a manipulation to the MR signal, and then fitting physics-based models to the signal to extract quantitative parameters. So using this example, without going again into too much detail because it's not your background really, but you can, you also can't see that very well, but you can sort of set up kind of physics-based models of how you expect the signal to change over time, like this one here. And then you can collect data at a range of different delay times and try to fit the model to the data. This was an example where we found the model fitted quite well in the grey matter of the brain, but when we looked in the white matter, the model really didn't fit at all. So we realised that this model was incorrect in that situation. So a lot of my work has been on improving that model to take into account the movement of water from the blood vessel into the tissue, and then you find that the model fits the data much better. So this is quite old work, but more recently we've been looking at trying to actually quantify the exchange rate of water across the blood vessel wall. So it seems like more and more we're finding that the blood-brain barrier is quite critical to a lot of disease processes. So we're trying to develop methods to measure the dysfunction of the blood-brain barrier. And it's quite nice being able to continually develop MRI in this capacity, because if we are able to do this, we've got MRI scanners in every hospital in the country, so we can very rapidly then translate these measurements into clinical practice. So yeah, but just to give you an idea, so from this work, we were looking at blood flow, which is approximately the amplitude of this signal, and the transit time, the time it takes to reach that inflection point. And so you can fit these models to every single pixel in the image and get an estimate of a quantitative parameter, so blood flow, transit time. So we're turning, I suppose, just the pictures that you get from MRI more into measurements of brain physiology. So going from pictures to measurements. And yeah, it's been nice. So just a few examples of how we've applied this over the years to different aspects of clinical practice and clinical research. So I've got a colleague at the Royal Manchester Children's Hospital, Stavros, who implemented this technique there, and they use it routinely now. And it's just quite nice to see now and again he'll send me, some information where it's been useful. So this was one example where they're using it in children who suddenly have got brain tumours. And the conventional images that they would normally collect, so this is two examples here, where there's not an obvious difference, really. And it was only when they used the blood flow image from ASL that you could start to really see the differences. So in this example, there was very high blood flow that indicated a particular type of tumour, whereas in this case, it was really low blood flow, which indicated a more benign type of tumour. So it was helpful to, at this stage, I think they're just collecting the information to see how useful it is. But now I think they trust the information to the extent that it would influence how they manage the patients. So it's really nice to see that. We're currently using this now in a clinical trial in adults with brain tumours. So you can see this is the blood flow map, but soon you'll see, this is the tumour, and you can see that high perfusion around the rim. So that's quite useful to look at testing new treatments. So in this study, they're looking at applying radiotherapy before people have surgery. And we're looking at how the blood flow changes following application of that radiotherapy. And more importantly, can we predict who might benefit? Because the radiotherapy itself isn't very nice. So, it's good if we can sort of personalize the treatment. And then just the last thing is in dementia. So I'm doing more and more work in vascular dementia now, and also Alzheimer's dementia. So this is really some of the latest technology. So this is a simultaneous PET MRI scanner. So we can measure not just MRI and the nice information we can get from that, but also positron emission tomography at the same time, which can give us very specific information about particular molecules in the brain. So for Alzheimer's disease, this is really important because you'd get information on the buildup of amyloid plaques in the brain from the PET, and from the MRI, you can get the structural information, you can get the blood flow information, and all together, we're looking at how that can be most predictive of who will. So we're doing this in people with very mild cognitive impairments at very early stages. So looking at whether we can predict who will decline and who might benefit from new treatments, which happily are on the horizon now. So we've actually got, just skip to this, this study is underway at the moment. In fact, you've been helping me with this, haven't you? Yeah, so this is the all-in-one study where we're recruiting people sort of from a real-world sample, so people who are coming through memory clinics. We're getting them onto the study. We're doing actually just MRI at the moment. We're taking blood samples to get amyloid information. But looking, and we're following them up for a couple of years to see if those early scans could predict progression. So that's it about the science. I don't know if anyone's got any questions about the science. Okay, good. I just wanted to give you a few slides about what I did and how I got to where I am. So I was always really interested in the brain, but I did physics degree, but I always sort of maintained that interest. So if there were physicists or engineers in the audience, I was going to sort of say, you can apply that knowledge to understand the brain. I think it applies to any degree, though. I don't think you need to feel like you're too constricted by what you've done. If you're interested in other things, that there's plenty of opportunities. And I think one real critical thing I did do was the Masters in Neuroscience. So I worked with a lot of colleagues who also did physics degrees and didn't do that. And I think they are then a little limited in, you obviously can pick up that information over the years, but I think it's nice to have that dedicated year sort of studying something new. So again, you guys might want to do a Masters in computational neuroscience or something, just something a little different from what you've done before. I think it gives you just a different perspective on things. So I did that. This was actually, I'll just go through this first and I'll tell you about this. So I did, you work out how old I am now. So I did my PhD at UCL. And actually in the middle, I took a year out to do a Masters. It's a bit of a long story. And then I went back to do the PhD. I'll tell you a bit about that, actually. And then, so this is a very standard academic career. Caroline's got a more interesting career path, potentially. And then I did 3 years working in the Netherlands, 3 years at Liverpool, and then I've been in Manchester a long time. And it's nice at this stage to be able to experience working in different countries, different labs, learn different things. But this is perhaps not necessary anymore. Like it used to be that you had to move around a bit and experience different labs. I think it's more acceptable now to just stay in one place, and there's other reasons you might need to do that. And then there's the standard sort of career path. It would be here that I had my first permanent job, and then you sort of have to apply for promotion every now and again to try and sort of move up the ranks.
What was your first paper then?
Oh, my first paper. So that was actually on the ASL modelling work. So that was right back then. Yeah. Stop that.
But you're a professor there, so that's.
Yes, I'm going to say these slides are a few old. Yeah, a few years old. So I'm a professor now. I was a professor in 2023. Thank you. But yes, partly I stole these slides because I had to give a talk on resilience in academia. Because you always get pictures like this, all the success stories. But what I highlighted in that talk was like all the failures along the way, so which is just part and parcel of an academic career, really. So you've got to kind of learn from that and just move on, like
More so than
any other career. Yeah, take feedback positively. Endless rejections.
I mean, seriously,
yeah.
You have to take it as a positive in a way. Find something positive in everyone because there are many.
Yeah, sure. So I was going to focus on this very first one, actually, because I didn't get onto my first choice PhD programme. The other things along the line that I won't talk about so much. So I found it quite hard to adjust to scientific culture. So up to your stage, probably everyone always tells you, oh, you're doing wonderfully, everything's great, you just get positive feedback all the time, and then you get your first academic job and like everyone sort of shoots you down, says it's all rubbish. So you've got to get used to that. Think of it as positive feedback, not personal feedback. Not personal. I think that's the thing. They're criticising the science, not you.
I think that people who can't, have many colleagues and students who have never managed to get past that, it's not personal. And if you can't get past that, then this is not the place. I don't think it's the science, it's not you.
Yeah.
You have to be removed to some degree from the work. Yeah,
for sure. So, was my first paper rejected? In fact, it's probably earlier than that. First grant rejected. Yeah, like there's rejection all the way through, and it's just part of the job. Yeah. But I was just going to talk a little bit more about not getting onto my PhD program. So, I'll just tell you what happened. So I came out of physics. Hadn't done the Masters, just done physics, but thought I was great. I had all this positive feedback all my life. I was like, I can go do neuroscience. So I applied for these 4-year neuroscience posts at UCL. I think it's maybe the first time they'd come out, and got an interview. But they were like, oh, tell us about, a paper you've read in neuroscience, or tell us about this. And I hadn't done any of background reading. I just thought because I was good at physics, that would be good enough. I just wasn't prepared, so I didn't get it. What I did do then is I got a different PhD, working more on physics questions, like applying new measurements of MRI to the brain, but I made sure at least it was on the brain because I knew that's what I wanted to do. And then while I was in my first year of the PhD, I saw this opportunity to do an interdisciplinary year to study something else. And then I thought, oh, well, why don't I do a master's in neuroscience? And I was able to do that and then go back to the PhD. And, things kind of work out if you know what you want to do and you're dedicated. So I think I could have been much better prepared for that interview. Maybe I'd have got on the 4-year program, So do be prepared and do your homework for each opportunity. Think about who's interviewing you, what are they likely to ask. Don't be put off by rejection. And seek out alternative routes to your goal. And be aware of funding opportunities. Like up to this point, it's very clear what you've got to do to apply for university, etc. Next step, there's findaphd.com, which is really good. But other than that, there's opportunities all over the place. Some people will see them, some won't. You've got to put a bit of research in, I think, to find the right thing for you. And I think that it's hard to decide what to do. Is it what you're really good at? Is it the first opportunity that comes up? But I think you've really got to do what interests you most. If I'd fallen into a different PhD at that point, I remember looking at the biophysics of foot and mouth disease or something, I don't know. I don't think I'd have stayed in academia. I think I've stayed because I've done what I was always interested in doing. So I think that's probably the most important thing. Sorry, I'm taking too long. You're right. Yeah.
Taken the whole...
No, I haven't quite. So maybe I'll skip this bit. Yeah. I like my job.
I can keep mine brief.
It's interesting. Never bored. Work with new people. Have job security now. Downside is, the work does fill the available time. Often work in the evenings. There's a lot of pressure. There's a lot of rejection. So. Yeah. Do a PhD. Yeah, do a PhD. I think if you enjoy your undergraduate research projects, if you're interested to learn more, if you've got good ideas, so the next step is a bit more about being creative and having ideas. It's not necessarily being a brilliant academic, or top marks and everything. And don't be put off by rejection. And this is a good website actually. People are interested in an academic career.
I will say, if anyone does an MSc here in either the MRes or the neuroimaging and cognitive and clinical neuroscience, I do run a whole session on